Welcome everybody to infrared spectroscopy. We're switching gears here and starting an entirely new topic. Okay, I know you may think like I'm looking like the lady who's selling Campbell soup, Campbell chicken noodle soup for that matter, but we had to like really shine a light on me so you can see the slides here. Okay, so this is season 2, episode 1. Green screen and all. So there are a lot of changes here. We actually did 24 tries before getting to this one, and I hope this is going to work. All right. Okay, let's talk about infrared spectroscopy. Spectroscopy just comes from the word spectra, which is like the rainbow spectra. So everything, I mean, pretty much all energy is in a spectra. And we call it different names by how we feel it. For example, the visible range right here in the middle here is when the electromagnetic radiation interacts with your retina. And you can see, a color or an image because of the interaction between the visible range with your retina. We call this range infrared because we really can't see it. It's below red, the magnetic radiation, electromagnetic radiation, and that's basically heat. So we have sensors on our skin that can feel it, but we can't really see it. And same with microwave. So when you put stuff in your microwave and turn it on, the molecules are rotating. And so you can feel that, and we can feel that too. Okay, so this is kind of in the heat range. And then when you go over here, the electromagnetic radiation at this frequency can interact with your eardrums. Your inner ear canal goes through and hits your eardrum, and you can hear music or sound. So this is just radiation. The radiation is just coming out in different wavelengths and different frequencies. But the way we perceive it, we've named it different things. And this is ultraviolet, which also you really can't see, but it's like sometimes you can see UV when you go through at the airport when they scan and stuff, you may see some of this, okay, like a purplish glow. All right, we call that UV. So we can name the different regions here according to how we perceive it, and that's the difference is only in the frequency. Only in the frequency of the electromagnetic radiation. There's nothing else different. Now, energy basically is Planck's constant times frequency. And we know that frequency, what's new is c over lambda. And we know that c is just the speed of light. And we can write energy is equal to hc over lambda. But 1 over lambda is called wave numbers. And so let's say lambda is measured in centimeters, then wave numbers is going to be centimeter minus 1. And for infrared region, which is what we're going to look at in infrared spectroscopy, this range would be from 4,000 centimeter minus 1, that's the upper limit, to 400 centimeter minus 1. You go beyond this, you're creeping into the visible. You go below this, you're creeping into the microwave. So this is the region where you're going to see the infrared spectroscopy. What is actually happening in this region to the molecule? Let's look at that. Let's explore that a little bit. Infrared is in this region of the wave number. So over here, we can see some lines when you put a molecule in here. What do these lines mean? That's when you have a spectra in this region. What does that mean? Let's look at what's happening at the molecular level. Now, I don't know if you recall, but I did draw some lines like this last time when we talked about valence bond theory. Okay, let's revisit. So here, let's draw 2 of these. And we can then kind of see what's happening in the UV, infrared, and the microwave region using this. What does this mean again? This is just showing you that this is where the bond distance, and this is the energy, okay, potential energy. And this is the distance between atoms, let's say x, all right? So when we talked about how atoms are floating around, and when they get closer to each other, they start attracting. The nuclei of this is attracting the electrons of this, and the nuclei of this is attracting the electrons of this. And then whenever there's attraction, molecules love it, and they lose energy, and they get all happy and stable, and this is the best place, okay? They make a bond, and they stay there. They get too close, they get too stressed out, and they're squealing to come back here. So here, this is your energy level at that point. That's your bond energy and bond length. So let's look at what's happening inside the bond. Let's say this is the really stable bond length, equilibrium bond length. But it can stretch, and that's what happens when you shine some infrared on it. It starts stretching. When it starts stretching, its energy starts going up. Okay, after some time, we can't take it anymore, but up until this point, it's going to be stretching. So let's say this is your fundamental vibration, and then you're going to get, closer and closer, and that's like your max. This is 0, this is 1. So when you stretch, you will see that the energy is getting absorbed by this bond. And that's what the infrared machine shows, that it's drinking the energy in this region. So basically, you're going from this energy level to this energy level when you're stretching that bond. Okay? Now, in between, there are also other rotational frequencies. The rotational frequencies would be in the microwave region, okay? That's called the Raman spectra. So here, while it's stretching, it's also rotating. So you have rotational spectra and vibrational spectra. So here, the vibrational spectra is mainly where the infrared is. So when you go from here to here, you're also rotating. So you may not always fall back on the exact same rotational level. So therefore, there are possibilities that you'll go to a different rotational level. Therefore, when you absorb the radiation from here to here, instead of having a sharp peak, you may have a little broadening. Now, the broadening is going to be a lot more pronounced if you have hydrogen bonding and you have intramolecular hydrogen bonding, because now your bond length varies a lot more. So you'll have a lot of broadening. But basically what you're saying is this stretching. So this is your best, then it goes stretches, and goes higher in energy and keeps coming back. And that's what you're seeing here. Now, if all of the bonds stretched at the same frequency, well, infrared spectroscopy would pretty much be useless, because you're going to get just one peak. The good thing is different bonds are going to vibrate at different frequencies. So you will see a whole spectrum of this. CH bonds are going to vibrate at a different frequency than CC bonds. CC bonds are going to vibrate at a different frequency from OH bonds, and so on. Okay, so that's the really nice thing. So here's your rotational spectra in the microwave region. Here's your vibrational spectra in the infrared region. And if you put some more light into it, you can even go to a UV vis. Let's say you're going from here all the way to here. Okay, so this is going to another orbital. So this is going from, let's say, pi to pi star, electron transition. Now you can see this is going to require a lot more energy, which is why you got to drink a lot more energy or higher energy from the UV vis region. So this is your UV spectrum. And there too, you can go to different levels. So even there, you'll see very broad peaks. And it's really nice to see pi transition in UV spectra. Infrared gives you a lot more information though, because it's very bond specific, because each bond will have a different vibrational level. And so they're going to absorb at a different frequency. So you can actually go and see what types of bonds there are. You can, like, for example, if this is an OH, then you will see a CC differently, okay? And the broadening's different, the intensity of absorption's different, a lot of different variations when you have different types of bonds. So this is a very useful technique. Then the next one, obviously, when you rotate, you'll get microwave. But what we are interested in here is basically going from fundamental to the next one. Sometimes molecules can go to the next level, and that we will call overtone. So let's say going from here to here, you're going to absorb frequency, some frequency or wave number. Then going from there to there might be 2 times, and that's called an overtone. Okay, so you can get a lot of different variations. You can also get combination peaks where you have, let's say, nu1 plus nu2 differences and so on. But mainly we look at overtones, sometimes combination peaks, but the main peaks are just going from here to here, which is just, you know, the fundamental vibration frequency. And we have different modes of vibrational frequency, and that's what we are going to look at next. All right, in summary, we want to say spectroscopy is a method of finding out what's inside a molecule, the bonds, and maybe even the type of atoms, using electromagnetic radiation, a whole spectrum of it. So when you have a molecule, we are going to look at mainly UV vis, infrared, microwave, and radio. Radio is for NMR, and the others are spectra by themselves, UV vis spectra, infrared spectra, and Raman spectra. So all of those have to do with bonds, what's happening inside a molecule, what's happening inside a bond. Okay, so here's a bond, and you can have rotation, you can have stretching, and you can actually even break bonds. And that we are going to look at in mass spec where we're going to actually break bonds. So below that is just going to absorb radiation and either stretch or rotate or have electron transitions. Again, when you have electron transitions, you're going from one orbital to another higher energy orbital, absorbing energy, and then the detector will detect that and see what wavelength or frequency you absorbed and draw a graph for you. All right, and so that's UV spectra. Now, if you have molecules just vibrating, this is your perfect bond length. And let's say at equilibrium, and let's say that is your bond length. When you hit it with infrared spectroscopy, it gets into a fitness room, okay, and starts stretching and bending and doing all kinds of things. And here's when it stretches, keeps going back and forth, and then each type of bond will have a different frequency. And so the infrared machine here can detect what types of bonds are there and exactly at what frequency they are absorbing the radiation, infrared radiation. And it'll give you a whole array of bonds. And you can figure out from that what type of bonds you have. The important thing is the frequency of absorption. That doesn't change for a particular type of bond. An OH bond will always absorb at a certain frequency, or in this case wave number. It's always going to be around 3,300 no matter what. A H bond will absorb at a different frequency, and that is going to be always close to 3,000 no matter what molecule it is. So therefore you can see what the functional group is just by looking at those frequency numbers. All right, and so we're going to look at some spectra and try to identify what the molecule or what kind of functional groups we have using infrared. All right, so let's look at some spectra